Greetings, physicists. This will be a video on how to solve problems involving Newton's law of universal gravitation with some circular motion thrown in. Alright, we've got this first one here. This is an estimation problem. Those are always fun. Estimate the magnitude of the gravitational force between you and a student sitting a little over half a meter away. So let's draw this. Here you are. Here's the student half a meter away from you, or 0.6 meters away from you. Okay? And they say to estimate the magnitude of the gravitational force between you. So when I think estimation, especially about gravity, I'm thinking powers of 10. That's really what I care about. How many powers of 10 are they going for? So, average person probably has a mass of somewhere about 100 kilograms. Maybe half of that, but that's fine. That's the same order of magnitude. So we could say that each of your masses is equal to 100 kilograms, or 10 squared kilograms. This is 0.6 meters. That really rounds to 1 meter, or, well, let's just do it as 1 meter. You could do 10 to the 0, but that's fine. And we're going to call that the radius between you. Whenever we're talking Newton's law of gravitation, instead of a delta x, it's an r. And then we have g. Big G is, of course, 6.67 times 10 to the minus 11. And that can round to 10 times 10 to the minus 11, or, I'm going to give myself some room, that rounds to about 10 to the minus 10-ish. So the force between you, if we're estimating, big G is about 10 to the minus 10. Each of your masses is about 10 squared. And over the radius squared, which is 1. So that won't matter. So 10 to the minus 10, 10 squared, 10 squared. So we got 4 positive 10s and 10 negative 10s. So the leftover will be about 10 to the minus 6 newtons. So you all, when you're about a meter away from each other, you all are exerting a force on each other, gravitationally speaking, of 10 to the minus 6 newtons. Why don't you feel this force? Well, because that's what 10 to the minus 6 looks like. 1, it's a decimal, not a comma. 2, 3, 4, 5, 6 newtons. That's about how hard you pull on the person next to you. So, to put that in perspective, if you were floating in space next to each other, we want to know how long it took you to get to a velocity of 1 meter per second. That's like walking velocity, just by pulling on each other. So if you were a meter away from someone floating in space and you accelerated them to 1 meter per second, how long would that take, you wonder? So let's put that in. V equal V naught plus a delta t. Well, V naught is 0 if you start from rest. And the acceleration is going to be based on F equals ma. Well, that's the force of 10 to the minus 6, and we're estimating here, divided by your mass, which was 10 squared. And so that's going to reduce it even further, so you have an acceleration of like 10 to the minus 8. So we can plug that in and solve for t. So to get to a velocity of 1, if we divide by acceleration of 10 to the minus 8, you would get 10 to the 8th seconds. Or 1, 2, 3, 4, 5, 6, 7, 8 seconds. 100 million seconds. And I think there's only like 30 million seconds in a year. Right? Yeah, 3 times 10 to the 7th. So it would take you, if you were a meter away from someone, and it would take you an estimated 3 years to accelerate that person up to a speed of 1 meter per second. That's how weak gravitational forces are, just to give you an idea. So very often the gravitational force is referred to as the weak force, because you need a lot of mass to achieve any acceleration. You need an Earth's worth of mass, a planet's worth of mass, to get a decent acceleration in this town. All right. That's a fun one. All right. Number 2, find the gravitational force of the Earth on a 60 kilogram person. So this will not be negligible, and it also doesn't say to estimate, so we have to put in real values here. So we're going to be using, we have a 60 kilogram person, so we'll say mass 1 is 60 kilograms. They don't give us any other given, so we know we're going to be using the universal gravitational constant, g, which is 6.67 times 10 to the minus 11. We need the mass of the Earth and basically the radius of the Earth. If we think about it, the radius of the Earth is here. You're standing on the surface of the Earth. This radius is gigantic compared to like you or maybe half a meter. So we can use the radius of the Earth and not be off by many sig figs. So if you don't happen to know the radius of the Earth, you could just Google it, but it is 6.3 times 10 to the 6th meters, about 6,000 kilometers. And then the mass of the Earth, again, you could just Google it. Give myself some room here. But the mass of the Earth happens to be 5.98 times 10 to the 24th kilograms. So the gravitational force, which is what we're searching for, will be g, mass of Earth, mass of person 1, divided by, this is the radius of the Earth squared. And we're not going to have to solve that. The f is already solved for, so let's just plug everything in. I'm going to need a lot of room here. G is 6.67, 10 to the minus 11. I'm not putting in units, but everything we've had so far has been in kilograms and meters, and so is G, so don't worry about that for this one. Kilograms, you, or the person, are 60 kilograms, and the Earth is 5.98 by 10 to the 24th. I told you I wasn't going to do units, and I went ahead and did them. What a hypocrite I am. All right. Clean that up. On the bottom, we have the radius of the Earth, which is 6.3 times 10 to the 6th, and I am going to have to square that. My recommendation for you, for any time you are solving this problem, like a universal gravitation problem, or any physics problem that involves lots of powers of 10, is not to type the powers of 10 into your calculator. I have seen more mistakes because people try to put powers of 10 into their calculator, and it takes very specific language to make it work, especially if you haven't practiced with your calculator. Syntax errors, they call them. So to avoid those kinds of problems, and besides, you can do that very quickly on your own, right? You have 24 tens here. You have negative 11 tens here. We can put a decimal here, and that gives us another positive power of 10 on top. If we turn that into a 6, you have 6 powers of 10 squared is 12. So I'm going to have 12 powers of 10 on bottom. I'm going to deal with that all right now, and then I don't have to deal with it again. And I wrote 10 here, but that's really just 1 power of 10 right there. So I have 24 on top minus 12 on bottom. Cancel that out. This is going to be 12 on top. I have 12 on top, 1 here, and minus 11 there. So I'm left over with 2 powers of 10. See how quick that was. Way faster than it would even take me to type it into the calculator, and probably more accurate on average. So let's take the numbers then that are not tens. This is 6.67 times 6 times 5.98 on top. Let's make that look like a decimal and not a multiplication. On bottom it is 6.3 squared. That I can type into a calculator, and I just have to multiply it by 100 when I'm done. So let's do that. 6.67 times 6 times 5.98 divided by 6.3 divided by 6.3. And I get, about 6. 6.03. So 603 times 10 squared is about this many newtons. And we expect that, right? For a 60 kilogram person, if gravity is about 10, then we expect to get about 600 newtons of force. This has been rounded. I think this number has been rounded. I think it's actually 6.35. So this number will be slightly smaller which would correspond to a 9.8 gravity. But this is fine. This is all good. 603 newtons of gravitational force. So we can prove, this is not really proof, but this is reinforce why, or reinforce the idea that Newton's law of gravitation can be used to find a force between two objects. Awesome. On we go. If you didn't know it, Mars has 2 moons, and the small one, Deimos, is very small, in fact, only about 6 kilometers radius. And we want to put something in orbit around Deimos. So we want something to be going in uniform circular motion around Deimos. Now this problem specifies a very low orbit. What's a very low orbit? I don't know. That's tough. So what I'm going to assume they're saying here, and because Deimos is so small, I'm going to assume what they mean by a very low orbit is basically at the surface of Deimos, or so close to the surface that it's not statistically significant, that we're within a sig fig. So let's go ahead and say that the radius is actually the same as the orbital radius in this case for your projectile. So we want to make this projectile move around the orbit and orbit Deimos in uniform circular motion, and how fast do we have to make it go? So give me some givens. I've got the radius, 6.3 kilometers. I'm going to change that right now to meters, so I don't have to deal with that later. That's my R. Mass of Deimos is 1.8 times 10 to the 15th kilograms. That's in the correct units, and I'm just going to say mass of Deimos. All right, and I don't have the mass of the satellite, but that probably isn't going to matter to me then, I assume. So let's see what we can't do here. Well, we know that the force of gravity between the satellite and the object is going to be G, mass of Deimos, mass of satellite, divided by, in this case, the orbital radius, which we're going to say is r squared. We're using this r. But we also know this, for uniform circular motion, we have that F, the centripetal force, right? That's what causes a uniform circular motion. In this case, it's going to be the gravitational force that causes the centripetal force, is equal to mv squared over r for that object. And in this case, that m is the satellite. So these two are the same thing. This gravitational force causes this centripetal motion. So let's set them equal to each other. We will say that G times the mass of Deimos times the mass of the satellite over the radius squared will be equal to the mass of the satellite times its velocity squared divided by that radius, that orbital radius, essentially. Well, a lot of things are going to happen now. Look at this. Like I predicted, mass of satellite will cancel, and that's good because they didn't give it to us. The orbital radius, or at least one of them, will cancel. And I need v, so if I want just v, I just have to square root this side. That's not too bad in terms of math, right? That's just the square root of g, which is 6.67 times 10 to the minus 11. The mass of Deimos, which was 1.8 times 10 to the 15th, over the radius of Deimos, which was 6.3 times 10 to the 3rd meters. All right, let's do some algebra. 3 tens on bottom, going to cancel with 3 tens on top, leaving 12 positives, 11 negatives. Again, don't put that in your calculator because that's just 1 10 left over. So easy. So all I have to do is take the square root of this times this divided by this. So I'm putting that into my calculator. 6.67 times 1.8 divide 6.3 and then take the square root. Actually, I need to not forget to put that 10 in there. That 10 is technically in there with everybody else under the square root. So when I do that and I take the square root of everybody, I get 4.3 meters per second. 4.3 meters per second. What is that? 10 miles an hour? That's nothing. You guys can run that fast. So now you couldn't on Deimos, because part of the reason you can run so fast on Earth is because we have so much gravity. So getting up to speed and trying to sprint off of the side of Deimos and put yourself in orbit might not work the way you think it is, but you could certainly throw that fast if you were standing on Deimos. Although I think when we get to momentum, you'll find that if you were to throw an object fast enough to put it into orbit, you would probably launch yourself backwards on Deimos pretty far, simply because it doesn't have much gravity. So it would be very cheap to put a satellite into orbit around Deimos, but you would have to be careful yourself if you were there, because you could literally jump off of the planet and just be gone and go off into space. All right, do number 4 here. Oh, I like this, a ranking question. Rank, in order from largest to smallest, the acceleration due to gravity on the surfaces of these planets. Well, we only have a couple of variations. We have mass 1 and twice that mass, and then we have a radius and a twice that radius. So which is going to have the bigger effect on the gravitational force? Well, remember, the force is proportional to the mass of the planet, but it's also proportional to 1 over r squared. So if you double the radius, you actually reduce the force by 4. So doubling the radius is going to have the most effect. So the one that's going to have the smallest gravity is the one with the largest radius and the smallest mass. So that's this guy here. So C will be last in line. So the ones with the smaller radius, A and B, should have the larger gravitational force, and between them, the one with twice the mass should have the most gravitational force. So let's put that together. So we'll say that B has the most gravitational force. A has half the gravitational force of B, because it has half the mass of B with the same radius. D has twice as much mass as A, right? If we're comparing these two, it has twice the mass, but it has twice the radius, which is 1/4 of that. So if you're getting you're increasing the mass by a factor, or the contribution of the mass by 2 times, but you're reducing the radius contribution by 4 times. So D actually has half the mass, or half the force, or the acceleration at the surface, as A. So D will come next. And then C has the same radius as D, but half the mass. So C has 1/2 of D's acceleration. So we're going down by half steps. From B to A, you get half the gravity. From A to D, you get half the gravity, half of A's gravity. And from D to C, you get half the gravity. Good times. So then you could ask yourself, what is the relationship between C and B? Well, it has half of B's mass, and then it has half of B's radius. So that's a half contribution from the mass and a 4th contribution. Well, a half times a 4th, so C has 1/8 of the gravity of B. All right, and I believe this is our last one. This is the hard one. Communication satellites. So you can only do this, you can only get this type of satellite at the equator, because any other place that you try to make a geosynchronous satellite, the Earth will turn relative to it. But if you launch a geosynchronous satellite at the equator, you can set it up with such a height and such a speed that it appears to remain stationary. And so if it casts a shadow on one spot on the Earth, that shadow won't move. It'll stay right there on that little piece of land or that little piece of water. And I think water is more likely at the equator. I think there's more water than land at that latitude. Anyway, let's do this. So we're going to have a couple of things here, and they don't give us any givens at all. So we're probably going to be using this equation. F is equal to G mm over r squared, and we're interested in that radius there. And we're probably also going to be using the centripetal force, which is m v squared over r Well, let's just make sure. And because we do know that it's the Earth, we can say that one of these is the mass of the Earth. Here it's the mass of the satellite, and here it's the mass of the satellite. And this would be the, well, it's not actually going to be the radius of the Earth. So we'll need a period in there as well. And so if we do the same equation, F equals the mass of the satellite, we can do it in terms of period, which is 4 pi squared r over t squared. That's another way to write this one. In fact, I think that might be our better bet. Well, let's try this then. We know the mass of the Earth is going to be equal to 5.98 times 10 to the 24th kilograms. And the period we know as well. We know the Earth turns once, and in order for the satellite to remain stationary over that point, it has to go around the Earth in the same time period, and the Earth turns once every 24 hours. You know, times 3,600 seconds if you wanted to get it into seconds. Times 3,600, seconds per hour. All right, let's see what we can't do with all those. First, I'm going to try and set those two things equal to each other, the force, the gravitational force and the centripetal force. So I can do G, mass of Earth, mass of satellite, over that radius, which, yeah, that's what we're looking for. The orbital radius, so this is not the Earth's radius, over r squared, is going to be equal to mass of satellite times 4 pi squared, and this is the same radius, divided by the period squared. And look, mass of the satellite doesn't matter. You can launch a tiny little satellite or a giant satellite, and it will require the same sized orbit. And I know the mass of the Earth, and I know G, and I know period, so the only remaining variable is r, so let's solve for that r. I'm going to multiply by r squared on both sides, and that will cancel here, and I'll be multiplying r squared here, so I will get G. And I'm going to multiply by t as well. So G times the mass of the Earth times the period squared, I don't know why I put the 2 down here, it should be up here, is going to be equal to, I'll go ahead and divide by that 4 pi squared. 4 pi squared times, well, what's left on the right side is that r cubed. So to get that r cubed, to get r, I'm going to have to take the cube root, the cubed root of gm, mass of Earth, period squared, over 4 pi squared. All right, let's, oh no, not that, this. The struggle is real. There, that's all I wanted. Okay. Cubed root. I'll put the cubed root on after. This is 6.67, 10 to the minus 11. Everything was in meters and kilograms, and so we should be okay. All right, that's G. Mass of Earth is times 5.98, 10 to the 24th. And the period of the Earth is 24 times 3,600, because we want everything in seconds, over 4 pi squared, and that will be cube rooted. Ugh, what a problem. Now, let's see how many 10s we come out with here, and if they are weird, I will show you a way to deal with them, because they're under a square root this time. So, I have 24 10s here, and minus 11 should give me 13 left. So there are 13 10s currently. Your pro tip for the day is try to get your 10, if you're under a cubed root, try to get your 10s to be a multiple of 3. If you are under a square root, try to get your 10s to be a multiple of 2. All right? And the reason is, the basic reason is that the cubed root of, like, x to the 6th, for instance, is the same as saying x to the something, x to the n times x to the n times x to the n equals x to the 6th, right? And what is n? So the cubed root of x to the 6th is x squared. But that only works, right, or that only comes out to a nice round number, I should say, if the number under the square root is a multiple of the factor of the square root. So I'm making sure that I want to get this 13 that's not divisible by 3. I would get like a square root of 10 to the 13 is like 10 to the 3.3, which is, no, don't do that. So I'm going to take this decimal here by the 3600 and just move it and make it 36. That's going to give me 2 more 10s, so I can make this 15. And when I square root this, my powers of 10 left over will be 10 to the 5th. Cool? That's just something that will make your life easier. So now the 10s should all be gone. Those 2 zeros should be gone. And what I'm putting under the cubed root is 6.67 by 5.98 by 24 by 36 divided by 4 pi squared. So a lot of stuff to plug in. A lot of stuff in there. And what I get out of here is 423 times 10 to the 5th, but I'm going to move the decimal over and make that 4.23 times 10 to the 7th meters. Good, because if it was 10 to the 5th, it would have been inside the Earth. The Earth's radius is 10 to the 6th. So, yeah, that's about a kilometer or so above. No, excuse me. Ignore me. That's a lot farther. It's like, I think it's 10 times the Earth radius above the Earth. So pretty high up, and it turns out that's a lot of people that launch satellites aren't launching them that high anymore. It's novel to have a geosynchronous satellite, but you can do a lot more with satellites that are closer down. All right, there you go. Hopefully this was helpful to you in solving gravitation problems and circular motion with gravitation combined.